Anyway, so let's talk about decentralization and blockchain. So before I jump right in, who am I to talk about that? I'm a software engineer, 15 years or so, working on back-end, front-end, mobile stuff, the whole shebang. For the past 2 years, I've also been a digital nomad. So as I said, I don't have a fixed home base. It's like I'm roaming around all year. Currently sort of stuck in New Zealand. I dove into crypto world back in 2016. Basically got right into the Ethereum ecosystem and yeah, started from there. After that, I spoke in a bunch of developer conferences, especially in Belgium, in France, in Poland, DevOps mostly, to try and make developers aware of the opportunities and like make it as accessible as possible. And based on that experience, with a friend of mine, actually the one with whom I do most of the public speaking, we also created an online course on Udemy where we have like 15,000 students right now. And because it became more and more difficult to update the course material because of everything changing so rapidly, we transformed the content of the course into an ebook, and that's our main point of focus right now. And yeah, my what I call my perpetually unfinished side project is a new sort of dating app. I mean, we as developers, we all have those. So by this point, I guess most of you, especially if you're here, have heard of Bitcoin, right? Probably heard that it's the digital currency of the internet, that it's mainly for fraudsters and scammers and ransom money. You maybe have heard of the fact that there are other cryptocurrencies. Currently, I think it's more than 2 or 3,000 of those. And as developers, you've probably heard that Bitcoin is bad and that actually the technology behind Bitcoin is good, but Bitcoin, nah, that's a bad thing. My goal today is to show you that this whole cryptocurrency thing is kind of the visible tip of the iceberg, and that cryptocurrencies are to blockchain what email was to the internet. It's a very impressive first application. It's like a proof of concept. We still use it to this day, despite its many flaws. It's still everywhere, but of course we've extended the applications far beyond that, and that's basically the case for cryptocurrencies and blockchain in general. So there's a lot of stuff that's already happening under the surface that's kind of going off the radar for a lot of developers, and that's why I like to go on a little dive to see what's under the surface and what will be available soon and hopefully will surface up for most of us. So basically, if we come back to the core problems that software is meant to solve, the main one, I mean, one of the main ones is definitely collaboration. So how can we share information and work together to reach a common goal? Sorry, I forgot to switch my slides now. Yeah. So how can we work collectively on that information to make it useful and to reach a common goal? And yeah, the easiest way to do that is to use, I would say, a traditional client server kind of architecture for applications, where you have a bunch of clients that interact with the server through the internet. This server can be in a cloud made up of many servers, but from the standpoint of users, it's all behind a single address, a single URL and everything. So it's pretty transparent. And this server is usually a gateway to access the data behind it, so in a database. And so this server provides a bunch of services like authentication to check who can access the data, authorization to decide who can do what with that data. And it also handles collaboration with other servers if necessary. So for example, payments and that sort of things, and like mashups with other APIs and stuff like that. So that's like in the most traditional way that most applications are designed today. And well, it has a lot of benefits, of course, and that's something we all know and love, but there are a bunch of issues. Um, the first one is, what if the server fails and ends up being offline? Then at this stage, well, obviously, um, it's very complicated to collaborate because, well, clients don't have access to the server anymore. And also, uh, we've managed to like alleviate that problem quite a bit with redundancy and with cloud computing and stuff like that, having fallbacks all the time. But it still happens, including to very big applications. Think GitHub, think even Amazon Web Services has had those cases of completely going offline, even for a few hours. For some applications, it can be very problematic, especially when it's an infrastructure provider itself, and then all the applications built on top suffer from that disconnection. And the problem also with this kind of technical fault is that it can happen that data is lost in the process and irreparably lost. And again, that data is kind of the basis of the collaboration, the whole collaboration thing. So it can be really problematic. And here I'm just talking about technical failures, but what about banning and stuff like that? Right now, there's a big debate around the banning of TikTok in the US, for example. Um, it creates like big issues of, can the government really do that? Well, with a centralized application like that, it's pretty simple because you just have to shut down the companies who operate the servers, basically. And yeah, it's very complicated for those companies to have like infrastructures in several countries and like to mitigate those kinds of issues. So there's technical issues, but also just pure censorship and yeah, banning basically. Second big issue is that all this data centralized in one place creates a big honeypot for attacks. Especially if you start storing critical data like financial information, credit card data, any kind of personal information. We've seen with Equifax, the kind of the disaster that was there. There's been, of course, a bunch of those attacks over the years, and it's directly related to the fact that all the data is stored in a very small number of places, and so whoever has access to the inside of that system can get access to the data and do a lot of damage with it. Plus, there's a lot of information in there that is stored just in case. Nobody knows really why it was stored there. And since it doesn't cost that much because storage has become so cheap, yeah, there's a lot of surface for attacks as well. And yeah, probably the most recent example of that is what happened with Twitter a few weeks ago with the big accounts where there was a god mode on the server and somebody with social engineering managed to have access to all that data, and like we don't even know the full extent of what's going to be possible with that, because for a few hours some people had access to email addresses and phone numbers of a few huge users like Bill Gates and stuff. So yeah, we don't know where this will end. Next issue is kind of more a problem of trust, I would say. And that's the fact that we don't know the extent of how much information is gathered and stored in that database. So how big is this arrow actually? We share the information that looks useful to us for collaborating, but then we don't have any visibility about what the server is actually gathering and like cross-referencing in all directions. And also because it can easily collaborate with other servers, and that without us knowing, we don't know what they do with the data. Well, we have an idea, but it's really hard to kind of have some transparency and some yeah, accountability when it comes to how the data is gathered and used. And that's like typically the case of data hoarders like Facebook and so on. So that's also a big issue in terms of privacy, of course. The next issue that is really problematic is the fact that usually, again, this one of the responsibilities of this server is to check who can pass or not, who can do what with that data, which can either be poorly done, like there can be security holes everywhere, and it's really hard to audit until an issue actually happens. But also, it can also be used as a way to censor all the data that's on there. So influencing debates, making sure that certain users can do certain things and not others. Again, if we come back to the example of TikTok, there's a very well-known phenomenon that they call shadow banning. So basically people are sort of banned, but not really. And the only way they can see it is through analytics because they have less views. But we don't know exactly why they are banned. Is it because of opinions? Is it because of less popular content? Is it revenge for something? We don't know. So there's a lot of opaque things happening in there. And that can be a big issue, again, in terms of censorship and freedom of communication and collaboration on those platforms.
Right. Right.
So overall, the benefits of centralized applications is that they're relatively easy to set up. Again, it's an architecture that we know very well. We have all the software, all the tooling, all the monitoring right now to make that setup as easy as possible, including in very complex cases where you have cloud stuff and like Kubernetes and whatnot. It's also widely understood by people, including by end users. So users know that they have to type in a URL to access a website. And then if they want to authenticate, the username password thing is pretty well accepted now. People are very familiar with that. So the whole user experience is pretty standard across different applications. And as we'll see why it matters when we come to talk about decentralized applications. It's very easy to synchronize data because everything is in one place. Or at least there's the server that can integrate data easily from different sources. And so making sure that the data is consistent is pretty straightforward because there's easy control by one or very few entities over how the data is stored and how it can be modified. It's also very easy to control access to that data, again, because there's just one door, one entry point, or very few of those. So it's pretty straightforward. I'm pretty sure that anyone who's worked with SSO or any kind of authentication system will not be happy about that easy to control access to data, but still, in most cases it is. And it's easy to integrate with other services through APIs, microservices, whatnot, to just integrate one server with others. Also, it's pretty easy to scale up. It's basically all about adding storage or processing power to your server so that you can welcome more users and more, like have more bandwidth basically to serve more people. And it's easy also to build business models around all that data mining. So in most cases, if applications are free, then it incentivizes people to share that data, and then you can do all sorts of crazy things with that data and monetize it in very creative ways. And that's why the saying goes that data has become the new oil, because, well, it's being used for monetization a lot. Now, of course, as I said, and just to sum it up, there's a bunch of issues that are pretty important. This whole architecture is very vulnerable to faults, technical faults mostly, meaning that, again, despite all the redundancy and all the architecture and the design engineering that we can put around that problem, it's still very hard to completely suppress that problem. We can mitigate it, we can minimize it, but it will never disappear, which again, for some applications might be enough, but for others, not really. It's vulnerable to censorship. So you have no idea about how the information is controlled to a certain extent. Like there's big opacity around the rules around that. It's also vulnerable to corruption. And by corruption, I mean not just from hackers, but from governments, from third parties. It's very easy to do that sort of modification of data. And yeah, all the problem of how the data is stored, how much of it is stored, who has access to it, what people can do with it is a big problem with privacy. And those issues should, like, you can always think, okay, we can easily put some more engineering around those to kind of solve those problems. But those issues in particular are really specific to the fact that it's a centralized application. So long as it's centralized, it will never be possible to completely eliminate those problems. And those issues were kind of the front and center of the minds of a bunch of people who were trying to answer this question, which is, how can we collaborate without adding centralization in the middle? It's the easy way out. It's very familiar, but what if we could share information, agree on how to modify that information collectively without having to centralize it in any way? And again, there's a bunch of people who started to think about those issues basically in the early 90s. It created this whole philosophical, engineering, technical movement that we call the cypherpunks. And most of them were cryptographers and computer scientists from who had a long career designing the internet and all its protocols before. So those were people who really knew what they were talking about, and also who could see how the internet was evolving before everybody could. Like, they could see the centralization of big entities like Google and Facebook, and even before those actually happened, the trends were really clear to them. So they started to think about those problems, and the kind of the solidifying piece was what they called the Byzantine generals problem, which was kind of a thought experiment that they used to try and define what was the problem that they were trying to solve. And I won't go into too much detail about that specific problem. You can find a lot of documentation around it, but again, it's just a thought experiment to try and define the problem that we're trying to solve. And that big question led to nearly 2 decades of research, again, from the early 90s to the late 2000s. At some point, it kind of crystallized around one of the most fundamental and complex forms of communications, of collaboration, which was money and economic systems in general. And that's why the first solution that came up to that Byzantine general problem and collaboration without centralization issue was Bitcoin. So Bitcoin was essentially a currency system without central bank, without banks, without regulation, without centralization, without any institution to guarantee the way it works and to operate it. And yet it still had a predetermined and transparent number of currency units in circulation, something that was really easy to audit and verify. It was open to anyone around the world, so essentially censorship resistant. So long as you have an internet connection, you can easily join the Bitcoin network just by generating a pair of keys. You don't have to ask the permission to anybody. It's completely distributed, which means that it's fault tolerant. So if you want to kill the network, you actually have to kill all the nodes in the network. If you kill just a part of them, then so long as there's just one node that still runs the blockchain, it still works. And you can just add more nodes after a while and the system just recovers. So it's very fault tolerant. It has very clear rules to move money around that are enforced by cryptography. So it's corruption resistant as well. So it's impossible for a single unit, company, government to say, no, this is not allowed now. The rules are there, they're very explicit, they're open source, and they're all cryptographically enforced. So it's corruption resistant. And all of that still with a very simple data set, basically made up of accounts, balances of these accounts, money transfers, and that's it. And the extensibility of that network was by design. So the way that they designed specifically the language to organize the transactions was very limited, to minimize again the surface for attacks and stuff like that. But because of that, some of the people who worked on Bitcoin and with Bitcoin over the years, so again, this whole thing was launched in early 2009, and yeah, over the first few years, some people tried to kind of extend what you could do with Bitcoin to try and make it go further, and especially to try to implement kind of a new, it's not really a new concept. It had been around for a few years already, but that's the concept of smart contracts. And what are smart contracts? Basically, those are software transactions. So instead of having one kind of transactions across the entire network, only money transactions, saying, okay, if this account has a balance that's greater than the value that it wants to send, then I decrease the balance of that source account, and I increase the balance of the destination account by as much. And that was kind of the generic money transfer transaction that was the only one, or again, I'm simplifying here, but it's basically the main transaction, the main kind of transactions available on Bitcoin. With smart contracts, the idea is that what if we could use some of the aspects and the features of Bitcoin blockchain transactions and extend them and make them more generic. So in Bitcoin, transactions are auditable, they're immutable, they're signed, but again, they're just currency transactions. Now, if we generify the concept of transactions to operate on a customizable data set and a complete set of operations that you can perform on that data, then those characteristics of Bitcoin can be generalized to other applications than just cryptocurrency. And that's the whole idea behind smart contract. Again, this has been tried for quite a few years on the Bitcoin network itself. And then, some people realized that Bitcoin was too limited and we needed a new kind of architecture and system for that. And that's where Ethereum was born. So in Ethereum, which again is just another blockchain architecture and software system, there are basically three types of Ethereum transactions. The first one is just like on Bitcoin, you can move currency around, you can move money around. So send money from one account to another. That's very basic, it's still there. So basically Ethereum is, again, to put it simply, just an extension around Bitcoin. But in addition to that, you can also do two kinds of things. You can deploy a software service, which is just another abstraction for a smart contract, and put it and make it available at a certain address. And I'll show you what it means after. And of course, once that service is deployed, you can easily call functions on that smart contract to modify the data that it encapsulates. So those are the kind of three core types of transactions that you can do inside of Ethereum. So that was just a small introduction to explain where we come from and why Ethereum makes sense and like the historic context, basically. Now, I just want to show you what it looks like. What I'm going to show you now is the project that we created for the online training, so the Udemy training, and it's also the same project we use as a basis for the ebook. It's called ChainList, and it's basically like a decentralized version of Craigslist. Very simplified, of course. So it's kind of a marketplace where you can sell and buy articles, and yeah, that's basically it. So very simply, just to give you a general idea of what a smart contract looks like and what it can do and like the features that it offers compared to a traditional backend. So a contract is a singleton, single-threaded service. So whenever you deploy it, you deploy it at a specific address, and then people can access it by calling functions on it, knowing that each call to a function is single-threaded. So you don't have any concurrency issue, because basically calls to functions in the contract are packaged inside transactions, and those transactions are executed in sequence by Ethereum nodes. which has some impacts in terms of performance, of course, but also guarantees that we don't like step on each other's toes and have all sorts of concurrency issues that could be manageable in a centralized environment, but would be completely a nightmare in a decentralized context. So in this case, the code that you can see right now is Solidity code. So Solidity is a programming language specifically made for smart contracts on Ethereum. It's used in other environments as well, but it was really designed for Ethereum. There's a bunch of those programming languages for smart contracts, including on Ethereum itself, because Ethereum, the runtime environment for Ethereum is basically a virtual machine. So long as your language compiles down into this bytecode for this virtual machine, you're fine. So there's a bunch of them, but Solidity is definitely one of the most used. One of the reasons for that is it's very close to JavaScript, with a few influences of C in here and there. But it's pretty readable and easy to approach, even though it has some security gotchas that are really important. It supports multiple inheritance. So right now, this contract called ChainList extends only one other contract. So contracts are like classes, if you want. And the ownable contract makes it possible to associate a contract with who deployed it, and then to change even this special user who can do crazy things with the contract itself. And I'll show you what it means later on. So we can define custom data structures inside the contract. Again, this is very private, so everything you do inside the contract can only be accessed by this contract itself, not by the outside world. And this is just like the struct is just a syntactic sugar, basically, to make it easier for the VM doesn't understand anything about structs. It's just syntactic sugar. One thing that is important to realize is that blockchains are not meant to store huge amounts of data, because data storage is really expensive, for the very simple reason that since the whole system is distributed, that means that all the data of the blockchain is replicated on every single node of the network. At least that's the case for now, which means that every time you store 1 bit or 1 byte of information more in a smart contract, you replicate that by how many thousands of nodes there are on the network. So of course it's very expensive, and we'll see how this whole thing is mitigated. But if you want to store like an image or a video file or anything, you don't store it in the blockchain, you store it outside. You maybe calculate a hash or have a URL, and that URL you can store in the contract if you want. And the best thing is that if you can have a hash inside the URL that uniquely identify one version of a file, that's the best case. And there's a bunch of things that we can use to do that. You can store strings, integers, like very large integers, like 256-bit integers. You cannot store any floating points numbers, which is not a problem when you have these kind of integers, because then you can easily basically manipulate very small, you can multiply your floating point number by a certain amount and you're back to an integer. So that's the way we work with that. So that's just declaring a new data structure. And then these are the state variables. So state variables in a contract are basically the contract's own database. So that means that the contract is stateful. It has its own state. And this state can only be modified by the contract itself. You cannot change it from the outside. You cannot do crazy things with it. Only the functions of the contract itself can read and access that data. The next section is events, and those are just a way for certain functions to notify callers that something has happened. So it's basically like logging, basically, but a little bit more powerful than that. So because everything in a contract is asynchronous, so when you modify data, it can be very interesting to know, okay, this has been done, this has been done, this has been done, and react accordingly, maybe update the user interface and stuff like that. So basically we just define 2 events here, one for when we sell an article and when we buy an article, we associate a bunch of data with it so that it can be useful to the user interface. And then we have functions. So this one is kind of interesting because it's a function to basically make the contract unavailable, to kill the service, to take it offline. And that is public, meaning that it can be called from outside the contract itself. Functions that are not public are only internal functions. And it's marked with a special modifier that's called only owner. You can see that as an annotation of sorts. And this annotation is actually defined inside the ownable contract that we extend. So if we go there, the only owner thing is here. That's a modifier that verifies before running. So that's basically means that's the rest of the function to which this modifier is applied. And we just check that the caller of the function is the same as the one that deployed the contract. Again, that's only possible because I added this function. If I don't add this function, if I don't make my contract ownable, and I don't add the scale function, then the contract cannot be taken offline. So long as it's deployed on the network, anybody can use it. So that's one way of actually building software services that never die, that are impossible to kill. And there are some really big applications on the Ethereum network right now who work that way. So the original creators of those contracts, they deployed them, they verified that everything worked, and then they called a function that basically cut the branch they were sitting on so that they cannot take it offline anymore. And they've had issues with the FBI, the CIA, and everything, like asking them, take that offline. I can't, sorry, remove the possibility of doing it. So that's a pretty powerful feature. So the next function is sell article, and as you can see, it can take a bunch of arguments. It is public, again, meaning that it can be called from outside the contract. The rest is pretty straightforward, even for any kind of service. The first thing we do is validate the parameters, making sure that the prerequisites are met. And if not, so if that is not true, this require function actually throws an exception. And when an exception is thrown, the whole thing is canceled. The whole thing is, the state of the contract is reverted. So it's all atomic. And that's by design. It's the only way to do it. You cannot create crazy transactions and stuff. It's all completely atomic by design. Another important aspect also is that, as I said, every operation on the blockchain costs money. It incurs some transaction fees. And those transaction fees depend on the code that is run. If you store data in your state, it costs money. The more data you store, the more expensive it gets. If you collaborate with another contract, call a function in another contract, send money around, all those operations cost money. So whenever you throw an exception, all the money that you spent so far with the operations is spent. You cannot recover it. That's just a way to incentivize developers to be careful about what they do. And they don't introduce bugs, and they validate parameters as early as possible and stuff like that. So that's why we do all the validation first. And then once we have validated the parameters, we just update the state. So in this case, we have two, again, we just have an article counter, which is essentially sequence number that we increment, that we can use as an ID for articles. And then we store a new article. And for that, the very interesting part of that is this line. So we use a special object that we can access in every function that's called MSG. And MSG provides us with metadata about the transaction itself. So in this case, we can know, again, every call to a function is packaged, is wrapped into a transaction. That transaction is signed, like digitally signed. And then we, in the MSG.sender, we get the address of the account that called that function. So authentication is built in. No need to check anything. Again, we can use this msg.sender to check that the user has access to that function. We can use that data directly as we are doing it here. It's very powerful. And MSG has a bunch of other fields that can be very useful for business logic. So we create an article with a, so this is the buyer. So right now it doesn't have any buyer. So we just put 0 in there, like a null address. And we store the other information. And when everything is done and successful, then we emit an event to notify the watchers that something has been successful. So nothing crazy, it's very simple code, but it just shows a bunch of really interesting features there. Then there's a bunch of what we call view functions. So functions are annotated as view. There's a, it didn't used to be the case, but it's the case now. The compiler actually checks that those functions don't modify the state of the contract. So those are read-only functions. You cannot modify the state in any way. And this is just to return some data about the state of the contract itself. And this just returns one of the variables. This one is a little more involved because we're trying to identify which articles are still for sale. We just want to return the identifiers of the articles who don't have any buyer, basically. And this just shows that the language is still pretty basic and really low level. So what we're doing here, we just want to return an array of identifiers, but because arrays in Solidity are statically sized, we cannot create dynamic arrays. So we basically have to create a big array, put the identifiers in there. That's what we do with this loop right here. We put the identifiers in the big array, so there will be a bunch of unassigned elements at the end. And then we have to copy everything in a smaller array so that we return an array with just the right size. So it's very, it's not very readable. It's kind of not super maintainable, but that's the kind of idiosyncrasies we have to play with because of the language being so primitive, I would say. And the last one is probably the most interesting one, this buy article function, because you can see a new kind of modifier on that called payable. And that means that you can actually call this function by attaching some cryptocurrency to it. So that's the payment kind of system that's built into the architecture. So you can call this function and associate some native cryptocurrency. So that's only, in the case of Ethereum, it's called Ether. You can attach Ether to your transaction when you call that function. And that amount of money is added to the balance of the contract. So a smart contract has its own bank account, if you want. And as soon as you call it a payable function and you add some currency to it, it's added to the balance of the contract. And then the contract will be able, through code, to send that money around to other contracts, to other accounts, and stuff like that. And that's what we're going to do here. So again, there's a bunch of required to validate the parameters. I won't go into much detail here. It's pretty straightforward. As you can see here, we're still using the msg.sender to check that the buyer is not also the seller, because it doesn't really make sense for the seller to buy its own article. And also we are checking that the msg.value, which is the cryptocurrency that's attached to the transaction, is the same as the price of the article. If it's lower, if it's higher, and in case we just throw an exception so that the call is refused. And then once we have done all those checks, again, we can update the state by assigning the buyer and transferring the money to the seller. So again, this value, this amount, is taken directly from the balance of the contract and sent over to the address of the seller, which we recorded when we sold the contract, sold the article. And then again, we just emit an event. So that's pretty straightforward, but again, it goes to show a bunch of really interesting features of smart contracts. Here, if you look at the data, the way it's stored, So this field, this state variable, is not an array, it's a mapping. The cool thing about mappings is that those are virtually infinite mappings, in the sense that you can add data dynamically into it, because by default, every key is virtually assigned. So if you go check the value of a specific key, if there is something there, it will return an article. If you never stored anything there, it will just return 0. It won't tell you that the key doesn't exist. So the way that we store data here, we can actually have sort of a dynamic array. The only reason why I'm having to create those static arrays here is because we're working in memory. So I'm basically just going over this. Let me check. No, that's the wrong function I'm checking. Yeah, so I'm iterating from 1 to the value of article counter, which is basically the maximum value of my index. And I'm checking articles that are stored there to make sure that they have, their buyer is not 0. And if that's the case, I'm storing them in my temporary memory array. And that's because arrays that are created inside a function have to be statically sized. If you store data in an array in the contract state, those can be dynamic. So depending on whether you store your data in memory or in storage, which means in the state of the blockchain itself, you can do certain things with it or not. So again, this is really bad in terms of developer experience, because it feels like we go back to the old days of C, where we had to think about data memory allocation and where data goes and everything. It's kind of boring, but yeah, that's what we have to play with because of the language itself. And once we have such a contract, of course, we have to deploy it somewhere to make it available so that people can access it and call those functions. The way it works in a traditional application, of course, is that you will package this service somehow, and you will deploy it to a server environment, maybe AWS, maybe your Tomcat of choice, whatever, and it will be stored and deployed at one specific place. In the case of a blockchain, what you do actually is that you store the compiled version of that contract inside of a transaction, and that transaction makes the contract available at the central address. But you just send it to a single node, and then, like any transaction, this transaction will be spread around, broadcasted to other nodes in the network, like in a peer-to-peer fashion, until this transaction reaches a miner. And the miners are kind of the arbiters who say what gets added to the ledger or not, basically. And once it gets added to the ledger, then it is again broadcasted to all the other nodes, saying, now we have a new contract that's available at this address. All of this happens behind the scenes. We don't really care about it. All the synchronization between all the nodes, all the validation of the transactions, this is all handled by the blockchain itself. All we care about as developers is that we need to send this code somehow to a node. Now, the cool thing with development, of course, we don't have to interact with the real actual blockchain, which can be really cumbersome to use. There's something that we can use that's called basically a network emulator. And the one I'm using here is called Ganesh. And it basically creates like a fake blockchain with just one node, with a bunch of accounts that already have some fake ether in them. And then we have all this user interface to kind of inspect what's going on, the transactions that are sent, what's in them, the contracts, the events, and everything. So this is a really powerful tool. It's really fake. You cannot use it as a real blockchain, but it's really powerful for development. And then in addition to this kind of emulator, so that's kind of the iPhone simulator or the Android device of sorts. It's the same thing, same logic. And then the other tool that we're regularly using is called Truffle. And Truffle is kind of like the Maven or the Gradle of the Ethereum world. So it compiles, it deploys, it offers you infrastructure to test, to unit test your contracts, a bunch of tools to measure different things, to interact with contracts once they've been deployed. So it's a pretty nice command line tool. There's still not a lot of integration in IDE. So again, that's kind of the prehistoric times of this, but yeah. So this is again the emulator, and then inside there, I'm just going to show you what it looks like when we do the deploy itself. So I have my node running. It's ready to accept transactions. All the transactions are sent to the node using an RPC HTTP API. And then I can just do truffle migrate. I'm going to force compilation of all the contracts, ignoring caching. And I'm going to reset the state of the migration utility stuff. And I'm going to specify that I want to deploy it to my Ganache network. This is all in configuration files, by the way. And then what this does, it will compile my contract into Ethereum virtual machine bytecode. It will package that code into a transaction, send that, sign that transaction first, and then mine it. Actually, it's the node itself that will mine it. Let me show you. So yeah, what you can see here. So we have a bunch of information here. So we can see the different transactions. So in this case, we have this special contract that I didn't show. It's just like a utility contract. I won't go into too much detail about that, but this is the transaction that deploys our ChainList contract. So we have the hash of the transaction. We have the address at which the contract was deployed. So that's the address that we need to use now to access functions on that contract. We also know which block it was mined into. The account that did the transaction, by default, it just uses the first account it can see. The balance of that account. Gas used, that's a very important part. That's the transaction fees that I mentioned before. So when you deploy a contract to the blockchain, you're essentially storing the code of the contract in the state of the blockchain. And that's one of the most expensive operations there is. So the more complex your contract, the longer your code, the more expensive it will get to store. And so again, it costs money. It cost me 0.02 Ether to deploy that contract. But this is based on so when I pay transaction fees, this gas used is the number. It's basically based on the complexity of the contract itself. And this gas price is the price per gas unit in Ether. So I have to multiply the two to have the actual price to deploy the thing. And this gas price is really way below anything that's accepted on the actual production network right now. I think the average price right now is somewhere around 150, 160 Gwei. It's a subunit of Ether, by the way, Gwei. So yeah, I would actually pay more to deploy a contract on a real blockchain. That's what I mean. And yeah, that's basically it. And the cool thing with the emulator then is that I can go back to the Ganache thing right now, and I can see all the blocks that have been mined. So in this case, again, it's a fake blockchain, so it's not mining blocks regularly. It's only mining new blocks when there is a new transaction added. And right now it's mined 12 blocks. And in the last one, I should be able to see, no, that's actually this one. That's the transaction that deployed the contract. I can check it right here. Replacing ChainList transaction hash starts with E53F. That's the one, E53F. You can see this transaction is a contract creation transaction. And if I go inside there, I can see this transaction data. And this is the compiled code of my smart contract. Okay. And what else is there interesting? So now I can see also all the contracts that have been deployed in Ganache. I can even inspect the state. So right now, our ChainList contract has just been initialized, so there is no article for sale. We have the address of the owner. We can inspect really the state of this thing. It's not perfect. It's very buggy. There are a bunch of things that still need to improve on there, but yeah, it's still pretty helpful. And that's it. So that's what we can do. We can see in the blockchain itself. And then once we have done that, we can, even before we start to write any sort of front-end application to interact with the contract, we can already interact with the contract itself. So I can start a truffle console to just connect to that network with a command line interface. Anyway, and this will give me like a JavaScript wrapper around my contract so that I can call functions onto it. I can check the results and everything. And by the way, I can use the same kind of JavaScript wrapper for unit testing and of course also for my web interface. So yeah, I won't go into any more detail with that because I want to yeah, go back to the conclusion. The course itself is like 16 hours, so I'm just trying to condense as much interesting and valuable information as possible in that. So just to wrap things up, benefits of dapps, we have built-in payment system. I showed you the payable function system that makes it possible to, again, pay without having to integrate with any sort of gateway. Of course, it's only cryptocurrency payments, but still, it's there. We have built-in anonymous authentication and authorization. I emphasis on anonymous because we don't need to actually know the email address, the password, any sort of personal data. All we need to know is that certain accounts do certain things and they digitally sign everything they do. So we can follow them through different operations. We have complete auditability because every deployment and then every subsequent call to a function of a contract is audited in a transaction that is open and easily available to anyone, basically. So it's also impossible to deny that something has happened because you cannot change it after the fact due to the immutability of the blockchain. It's, again, possible to deploy completely unstoppable contracts, impossible to kill. So very good for reliability and guarantees that your contract will always be available. It's easy to check that the code matches the theoretical code, basically. You can just recompile your contract and compare the bytecode and make sure that the contract that you think you're interacting with is actually doing the same thing and nothing has been changed behind the scenes. And all the data stored in the contract is visible, which is both a benefit and an issue for certain kinds of data, of course. The main benefit is that it's impossible for a contract to hoard data without users knowing. Now, of course, there are some challenges associated with that. Transactions are super slow. Again, the typical comparison we make is something like the Visa or the MasterCard credit card network can process anywhere from 10,000 to 50,000 transactions a second without a break in a sweat. In the case of Ethereum, it's closer to 20 transactions a second. So we are like 3 orders of magnitude slower. This will change over time, of course, but it's still an issue to take into account. The network throughput is limited. Right now, it's an issue because if there is congestion on the network, then transaction fees go up. And that's why transaction fees are going up right now because there's a bunch of applications are getting very popular. Every non-view call costs money to the caller. So that's something that's really hard to explain to users, that all of a sudden they have to pay for the operations that they do that modify the data. Not something they're very used to. So in terms of user experience, it's kind of a challenge. Again, because of that, and also, yeah, because of the way that the whole system works, because of cryptography and everything, all the data in the state is visible. So yeah, you'd better not store critical data like health information and stuff like that in the state of contracts. And it requires a special kind of browser. We call that a Dapp browser. I didn't have time to show you that, but typically in Chrome or in Firefox, we use something called MetaMask, which is kind of a proxy that holds your keys, your wallet, and also connects to any network, and then does the forwarding, the signing, the security aspects of the transactions on your behalf. And again, languages and tooling are still pretty basic. So that's kind of a pain in the ass sometimes, but that's how it is. There's a bunch of changes that are upcoming. Ethereum 2 is currently being worked on and being deployed over a long period of time because it's a very big change. It has a lot of implications and it will change everything. It will change a lot of things to the way we develop contracts and the way we deploy them and what they can actually do. So that's something to keep in mind. But in the end, we'll have, thanks to that system, we should have faster and cheaper transactions. We should have a different kind of accounts called contract accounts, which allow for more sophisticated security and signature mechanisms. We will have stateless contracts, so that's a whole different thing that I didn't even dive in yet because it's still very in flux. We'll have a different kind of virtual machine that will make it possible to use more sophisticated and more powerful languages on top than Solidity. And then there's a bunch of UX improvements being worked on right now with wallets and having to pay for transactions and everything. So this is all being worked on. So there's a lot of things that are in progress. Yeah, I'm not going to go into that. But yeah, basically, again, I had just added all the links to the training on Udemy. Again, the training on Udemy, I don't recommend it right now. It's kind of out of date because the videos are super hard to update. So we put most of our focus on the ebook. And by the way, if you want to purchase the ebook, I created a code. You can use the code CodeControl in one word, and you'll get 25% off on the book.